We've learned some important principles of calculus in this course so far. How to plot functions, how to differentiate them, differentiate a product of functions, a ratio of functions, and also, most importantly, the chain rule. Well, it's now time to apply all the things that we've learned, and let's do that to a number of practical problems. Let's begin by looking at a cube that's expanding in size. Obviously, the volume of the cube is the side of the cube to the power 3. The side of the cube, L, is changing with time. In other words, it is a function of t. And therefore, V is a function of t because L is a function of t. In other words, we have a function of a function which we know how to differentiate very well. It is the chain rule that tells us that dv by dt is dv by dl. So you differentiate with respect to the function L, and then you differentiate that function L with respect to its argument t. dv by dl is of course 3l squared, and dl by dt for this particular case is 3 meters per second. So we'll just write 3, write the units later. And when L is 4 meters, this is 9 times 4 squared, that is to say 16, and this is 144. Now we must put in the units, and this is, of course, meters cubed divided by second. Of course, we could have had a situation where the length was changing non-uniformly with respect to time. So here is a situation where the length is changing in this way, 2/3 t cubed plus t. Then we can find the rate at which the volume is changing with equal ease. We have dv by dl into dl by dt. That's 3l squared. We know how to differentiate L with respect to t. That will just give us 2t squared plus 1. And that's the final answer. But what happens when the derivative of a function with respect to its argument is 0? In other words, when the function is not changing at a particular point. To understand this point better, let me sketch a curve that looks something like this. It goes up and up until it reaches a local maximum, and then it starts coming down until it reaches a local minimum and then goes up. Let's look at the slope at every point on this. So the slope is initially positive. Right now it's 1.71. It's becoming less. Now it's 0.92. Now it's only 0.25, and now it's become negative, minus 0.3, and now it's becoming more and more negative until it starts becoming smaller once again and becomes 0 or close to 0 before becoming positive. The next point is very important. You see that whenever we are at a maximum or at a minimum, as over here, the first derivative is 0. So you could say df by dx or f prime is 0 there, and f prime is 0 over here. Whenever f prime is 0, that's of special significance for a function. Now, how is one to tell the difference between a maximum and a minimum? That's easily done in this particular case. You see that the tangent was positive to the left. It was negative towards the right. In other words, the derivative of the function has gone from positive to negative, and that's exactly what the derivative of the derivative, in other words, the second derivative is. So for a maximum, the second derivative is negative. On the other hand, you see over here that you had the slope looking like this on the left. The slope on the right is positive. So at the minimum point, the second derivative is positive. Whenever you see this situation of f prime equals 0, it could very well mean that you are at either a maximum or a minimum. It's by looking at the second derivatives that you can be sure. Now it can be that when f prime is 0, that you are neither at a maximum or a minimum. This is an unusual case, but the unusual case is not all that unusual, as this example will show you. So here is a function that is sloping upwards. Let's look at the derivative. So you can see that the derivative is positive to the left. It remains positive, but now becomes very, very close to 0. Right now the slope is exactly 0. And as I move more towards the right, the slope becomes positive. So, although for this function we have a well-defined maximum at which f prime is 0 and a well-defined minimum for which f prime is also 0, at this point, in other words, for this function, we have neither a maximum nor a minimum at this point, in spite of the fact that f prime is 0 over here. Well, also actually f double prime is 0. This is what is called a point of inflection. Using what we have learned, let's calculate the maximum and minimum values for this function, x to the power 5 minus 3x plus 1. Not for all values of x, but just for those which lie within this interval. X goes from minus 3 by 2 to plus 3 by 2. The first derivative, f prime, is 5x to the 4 minus 3. F prime equals 0 means that x to the 4 must be equal to 3 by 5. Now, if x to the 4 is 3 by 5, there are only two values of x that are possible. Either x is 3 by 5 to the power 1/4, or x is minus the same. Obviously, if I square this, I lose the minus sign. X squared for this and x squared for this are both the same, and x to the 4 equals 3 to the 5. 3 over 5 is satisfied by this. So let's take the first case. In this situation, x is 3 by 5 to the 1/4. The first derivative obviously is 0. The second derivative, f double prime, at the same point, you can see from here, let me do this, f double prime is 20x cubed. If x is positive, then f double prime will be positive, and so f double prime is positive, which means that this could be a minimum point. We can put in 3 over 4 to the power 1/4 and find out what the value of the function is at that point. And if I do that, 3 over 5, I'm sorry, then we find that the value is 2.634. That I did with the help of a calculator. Let me take the other point for which x is minus 3 by 5 to the 1/4. And again, the derivative here is 0. We found that out from up here. The second derivative is negative, because when x is negative, then f double prime is negative. And if I take the value of the function at this point, in other words at minus 3 by 5 to the power 1/4, With the help of my calculator, I find that this is 3.112. So certainly this can be a local maximum and this can be a local minimum. But we've been asked what are the maximum and minimum values for the entire interval from -3/2 to +3/2. Let's just use our calculator for that. And so we have f at -3/2 having value -2.093. That's what my calculator tells me. Whereas f at 3/2 has value 4.093. So obviously the maximum value of the function in this interval is this, and obviously the minimum value of the function in the given interval is this. However, let's see if we've got the local maxima and minima correct. And so I'm going to show you a graph now. The graph of the function looks like this. Now, just to remind you, 3/5 to the power 1/4, my calculator tells me is 0.88. And so we have a minimum at 0.88, which is correct. It's this much. And there's a maximum at 0.88 minus 0.88, of course. That's over here. So whereas the absolute maximum is this, at 1.5 it is over here. At minus 1.5 you have an absolute minimum which is over here. In other words, at the endpoints the value of the function is bigger or smaller than at the local maxima and minima. Nevertheless, we've got the local maxima over here correctly. See, the derivative is 0 at this point, and we've got the local minimum correctly. You see that the derivative, the first derivative, is 0 over here. Let's take a second example. Here I have the function x plus 1/x, and we need to know what is the minimum and maximum in this interval between 0 and 2. Well, let's first look at what f prime is. That's 1 minus 1/x squared. And when x is either plus 1 or minus 1, this f prime will be 0. However, we are only interested in this interval between 0 and 2, and so we need not worry about the negative value of x. At this point, f prime is 0, and we can calculate f double prime, which from here we see is 2 divided by x cubed, and this at x equals 1 is positive, so we expect a local minimum. What will be the value of that minimum? Well, let's put in the value of x. We see that f at the point plus 1 is obviously 1 plus 1 over 1, which is 2. And so the minimum value of f will be 2. You can see that f at x equal to 0 is, from here, x plus 1/0, and 1/0 is not defined. It's a very, very large number. So the actual maximum value will be infinity. And this 2 is going to be the minimum. This sketch will indeed assure you that we are at a local minimum at x equals 1, and the value of that is 2. The value of the local minimum is 2. Let's now look at this function, f of x equals x plus 1/x squared plus 1, in this closed interval between minus 1 and plus 1. I'm going to regard f as a product of two factors, one of which will be x plus 1 and the other will be 1/x squared plus 1. So let's take the derivative, f prime. We differentiate the first, that is x plus 1, we get 1, divide by the second, and then we've got to keep the first one as it is and differentiate 1 over x squared plus 1, which is going to give us minus 1. Remember, it's 1 over x squared plus 1 divided by x squared plus 1 squared. And then I have to differentiate x squared plus 1, I get 2x. And so this thing is 1 over x squared plus 1. And then here I have minus 2x squared plus 2x divided by x squared plus 1 squared. And now one small further simplification. This is x squared plus 1 minus 2x squared minus 2x over x squared plus 1 squared. I could now just write this more simply as minus x squared minus 2x plus 1. So I'm just simplifying I'm just doing the obvious steps. And now it would be nice to write this as minus x minus 1 squared, and I've just written it exactly. I've made no change. The question is, when is f prime going to be 0? For it to be 0, I must have x plus 1 squared equal to 2. So f prime equals 0 means that I should have x plus 1 squared equals 2, and that is x plus 1 being equal to either plus or minus of square root 2. In other words, there are two places where the derivative of this function is 0. One of these is square root 2 minus 1, and the other is minus square root 2 minus 1. Now obviously this over here is going to lie outside of this interval, so we don't have to worry about this. X equals square root 2 minus 1. Well, square root 2, is 1.414, and so this is about 0.414. That lies within this interval. And so if we sketch this between minus 1 and plus 1, then the derivative will be 0 somewhere over here at 0.414. Now, let's ask, what is the value of the function at that point? So f at this value, square root of 2 minus 1, let's look at the top. This is obviously, look over here, if we put x equal to square root of 2 minus 1, we get square root of 2 divided by square root of 2 minus 1 squared plus 1, and that's square root of 2. I'm just simplifying a little more, and at the bottom we have 2 plus 1 minus 2 root 2 plus 1, and that's square root of 2 divided by 2 into 2 minus square root, and that's going to give us 2 into square root of 2 minus 1. Or just work this out, this becomes 1.207. That should be the extreme value, but is it a maximum or a minimum? Indeed, looking at this function f of x equals x plus 1 over x squared plus 1, you see that the maximum occurs at square root of 2 minus 1, so that's 0.414, which is over here, and the maximum is indeed 1.2 something, which you can see immediately from here. Therefore, we've seen that this first derivative being 0 tells us about the maximum of the function. We did not calculate the second derivative, of course, but we could have, and we would have found it to be negative. You see that indeed here the derivative is positive, here the derivative is negative. And you would have found that exactly at this point, d2f by dx squared, or f double prime, would have negative values. Here's a fairly straightforward problem, but one which is going to teach us something new. F of x is x minus 3 cubed, and we want to know its minimum and maximum values in the interval between 2 and 4. The first derivative is obviously 3 into x minus 3 squared. The second derivative is 6 into x minus 3. And so obviously we have the situation where f at the point 3 is 0. The derivative, the first derivative at the point 3 is also 0. And the second derivative is 0 as well. Of course, the third derivative is just 6. That's not 0, but we're not concerned with that. Let's also note that f at the point 2 is minus 1. F at 4 is plus 1. And so here's the picture that one has of this function. So let's make a rough plot. Here is 2, here is 4, 3. The function is 0 over here, also its first and second derivatives. It starts from here minus 1, ends up here at plus 1, and so it's got to go up in such a way that it becomes 0. Also its first and second derivatives become 0. So although I can't draw this very well, you see that here, at this point, we have the first derivative and the second derivative both being 0. So it's very flat over here. This point is the point of inflection. And so we do not have a local maximum or a local minimum for this function here, f of x. The maximum value is 1 in this interval. The minimum value is minus 1 in this interval, and there is no local maximum or minimum. Here's a straightforward application of derivatives, but it's something that one has to have a physical understanding of. So here is stone that is crushed into gravel that's coming up this way, and then it's falling down, you can see that, making a pile over here. The rate at which it is happening is measured to be 100t minus 2/3 t cubed. Now that's a formula, but we don't believe formulas until those give us some reasonable results. The first part of the question is, until what time is this formula reasonable? You see that when t is small, you can neglect this, so the gravel is falling at an increasing rate. On the other hand, as t becomes larger, this term starts to dominate, and at some point r will be 0. When r is 0, that means that 100t minus 2/3 t cubed will be 0, and so t squared, we can cancel the t's on over here and over here, so t squared will be 300 over 2. In other words, it will be 150, and that means that t will be square root of 150. So that lies between 12 and 13. And so you can trust this formula reasonably well until you get to 12 or 13 minutes. Now, why is it unreasonable? Obviously, once the rate becomes negative, you're certainly never going to have sand going the other way. You're never going to have sand going from the pile back into this machine. Now let's come to the second part of this question. What is the maximum rate of flow of gravel? That's very easily done, because let's take dr by dt, or you could call this r prime, whichever you prefer. And this is 100 minus 2t squared. At this time, that is to say, when r prime is 0, t will be square root of 50, which is 7 point something. 7 sevens are 49, so it's going to be pretty close to 7. If we put 7 into the formula, then we get the rate is 100 times 7 minus 2/3 times 7 cubed. And you can work out whatever that is. Let's solve some practical problems now. Here is a farmer who lives by the river. This blue is supposed to be a river. And he wants to grow grass in as big an area as possible. He's got only 160 meters of wire to fence his land off with. So he asks himself, should I do this? That is, put 35 meters here, 35 here, 90 here? Or should I do this? 40, 40, 80, that's also 160, or 50, 50, 60, again 160, or maybe something in between. How is he to find out? So, here is a problem in which he has a constraint. Let's say that this length over here is x, this is x, call this y. In that case, we have the constraint that he's got only 160 meters of fencing wire. So x plus y, 2x plus y has to be 160. The area that he can grow is, of course, this length times this length, x times y. But you see that y is not independent of x. From here, y is 160 minus 2x. So really, instead of writing x and y separately, we can get y in terms of x, and so this is x into 160 minus 2x. In other words, this is 160x minus 2x squared. Now, if he is to maximize his area, then he needs to take the derivative of a. If you take the derivative of a with respect to x, then a prime is 160 minus 4x. And for a maximum, a prime is equal to 0, which means that x should be 40 meters. How much land will he get from that? He'll get, well, obviously, if x is 40, that means that y will be from up over here 160 minus 2 times 40, which is 80, which is 80 meters. Let's see if this is a correct calculation and whether we've got a maximum rather than a minimum. Of course, now it is perfectly clear on physical grounds, but let's check it anyway, that this is a maximum. So a double prime from here, you can see, is minus 4. It's negative, the way that we said it should be for a maximum. But still, to reassure you, you can see that here is the maximum for this function y equals x into 160 minus x. It happens at x equal to 40, and the value of the function is exactly what we said it was. In other words, it was 40 times 80, which was 3,200. That's what is over here. We've helped the farmer who wants to grow grass. Now let's help the fish farmer. There are N fish in a tank. Just 4 over here, unfortunately. The more fish that you put in a tank, the more competition there is both for food and for air. Now, the fish farmer, has discovered a very useful formula. He's discovered that the weight per fish at a season's N is 500 minus 20 grams, where N is the number of fish. So if there were no other fish, if one fish was by itself, at the end it would weigh on the average 480 grams. But as you put in more fish, as N becomes larger, the fish don't gain as much weight. Should he put in more fish or fewer fish? For this, we have to do a calculation. Let W be the weight of all the fishes combined. So it's the number of fish times the weight of each of these fishes. So it's 500 minus 20N, and that's 500N minus 20N squared. The first term tells you that the more fish you have, the better it is. The second term tells you that you cannot put in too many fish, but exactly how many, so that W is the maximum. Well, let's take the derivative, W prime, that's 500 minus 40N. And if this is to be 0, then N obviously has to be 500 divided by 40. And this is 12.5. Now, what's the meaning of 12 and a half fish? Either you have 12 fish or 13 fish. In this case, you have 12.5. Well, that's because we've treated N as a continuous variable over here. In actual fact, if N is very large, let's say N is 1,000 fish, this would be a good approximation. But here, N being 12 or 13 is not very good, but it's not very bad either. Anyway, let's put in the best number of fish, that is to say, that which will maximize the total weight to be 12.5. In that case, we get W at 12.5, and this we can do a little calculation. It turns out to be 3125. Are we sure this is going to maximize rather than minimize? Well, again, on physical grounds, you would say it will maximize. What about on mathematical grounds? W double prime is, you can see from there, minus 40, and this is negative, of course. So again, we should be at a maximum. Now, just to reassure you, here is a sketch. You see that this maximum is occurring over here, and here we have N, or rather X in this case, doesn't matter. The variable is 12.5. That's where the maximum occurs, and it happens at 3,200. So indeed, we have helped out the fish farmer as well. Let's now help out the packager who wants to make a bottle or a container that will hold this 100 liters of water. The question is how to minimize the surface area. That minimizes the cost of the material for this container that we have over here. The bottle is actually very complicated, so let's approximate it, and this is quite reasonable, with a cylinder that has height h, it has a radius a, and of course the volume will be just this surface over here, pi a squared, times the height. So here's the volume. The surface will be this area, pi a squared plus pi a squared over here. and then 2 pi AH for the surface that's outside. That's, of course, 2 pi A squared plus 2 pi AH. Since the volume is fixed, from here we see that H will be the volume divided by pi A squared. In other words, you can take either H or A to be independent, but you can't take both of them because the volume is given to us as being 100 liters. So let's write a formula for our surface. That's 2 pi A squared plus 2 pi A times H, and H is the volume divided by pi A squared. And so we see over here that if A is large, then this term takes over. If A is small, this term takes over. And so the question is how to minimize S. Let's take the derivative ds by dA, or S prime. That's 4 pi A. And then here we have plus 2 pi V. Sorry, the pi's and the pi's cancel. So we just have 2V. And then we need to differentiate 1 over A, which is minus 1 over A squared. And what we get is 4 pi A minus 2V over A squared. If this is to be 0, in other words, if S prime, if the first derivative is to be 0, that means that A cubed must be equal to V divided by 2 pi. If A cubed is this, then let's see what H is. So A cubed is now that. H is V over pi A squared. And let me do the following trick. Let me put A over here and make this cubed instead of squared. So H will be V times A. And let me put below the value of A cubed, which is V over 2 pi. And so the V's cancel, the pi's cancel, and H is equal to 2A. So the point is that if we make the height equal to 2 times the radius A, we will achieve the minimum surface area. You can see that S double prime, let's calculate that if you like. From here it is 4 pi plus 2V, rather 4V over A cubed. This is positive. The important point is that the height must be twice the radius. And it doesn't matter if it's a 100-liter container or a 1,000-liter container, the volume has dropped out. Even with the very few tools that we've developed so far, we've been able to solve some quite interesting problems. And so in the next lecture, we're going to develop more tools by which to analyze functions with.